Hello and welcome to our 4 p.m. press workshop, NASA's MMS mission, Understanding Our Space Environment. Our speakers this afternoon are Jim Birch, MMS Principal Investigator, Southwest Research Institute, Michael Hesse, MMS Theory and Modeling Lead Co-Investigator, NASA Goddard, Catherine Goodrich, Student Research Scientist, University of Colorado Boulder, and Ian Cohen, Postdoctoral Research Scientist at the Johns Hopkins Applied Physics Laboratory.
Good afternoon. My name's Jim Birch, as you said, PI of the MMS mission. So we're here to talk about MMS, and the first slide over here, if it comes up, is a picture of our spacecraft. We have 4 large spacecraft that were launched in this past March, and now we've got all of the instruments commissioned and working properly, and we're into our science phase of a 2-year science mission. And is this slide supposed to come on? Oh, the space bar does that. Okay, well, there it is. And so the reason we're excited about it is that this mission is designed to understand a phenomenon called magnetic reconnection. In a minute, Michael will describe that in detail, but this is a fundamental physical process throughout the universe that causes things like geomagnetic storms, auroras, solar flares, flares on other stars, cosmic rays, gamma ray bursts, all kinds of phenomena throughout the universe. Also important in the laboratory. It's a large community of people that want to understand it, and there are different scales that it operates on. And we've done the job with other spacecraft at the larger scales, we call the ion scale, but it needs to be investigated at the smallest scale of the electrons, because this is where the magnetic reconnection happens. And so this was known, the mission was designed. It turns out that to go to the smallest scales, you need a very big mission. And it needs to be big because it's making measurements 100 times faster than have ever been made in space before for some of these particles. So the next slide here shows a cartoon of the Earth's magnetosphere. That blue ball in the middle is the Earth, and then these colored lines are magnetic field lines. So the Earth has a magnetic field, as we know. The Sun also has a magnetic field, and that's coming in from the left. The gold field lines have 1 foot on the Earth, and 1 foot on they have both feet on the Sun, sorry. These are solar magnetic field, they're attached to the Sun. These in here have both feet on the Earth, they're attached to the Earth. And this space is not a vacuum, as many people believe, but it's full of ions and electrons. And moving rapidly, the magnetic fields are also moving rapidly. And so when you get a magnetic storm, you get currents built up, and a lot of interesting things happen that collectively we call space weather. And space weather is very important, I think, as most people know, can cause power blackouts and satellite disruptions and the like. But if you ask, what causes space weather? It's magnetic reconnection. That's the cause of it. Where does it occur? In these 2 boxes. This is where the Sun magnetic field lines come in. It's flowing this way. The particles in the magnetosphere are flowing that way. When they collide, these field lines can interconnect, and you have field lines like this purple one. These purple ones have 1 foot on the Earth, 1 foot on the Sun. This is why the Sun can then energize the magnetosphere. And so we have to target this region here, and that's what we're doing now. In about 18 months, the orbit will go into the geomagnetic tail, and these field lines that were connected to the Sun, eventually they have to get unconnected from the Sun, or they would all be swept away. So we have 2 regions of magnetic reconnection. So next slide here shows, shows what we've done so far. This is that boundary. In this case, we're looking down on the equatorial plane, where the previous picture you were looking sideways, so it was north-south. This is east-west down here. This gold region is the region we're interested in, where we think we'll encounter this boundary called the magnetopause, and all these dots here, 1,800 of them, is where we've already crossed this boundary. And about half the time when we cross it, we see evidence that reconnection is going on, not right where we are, but somewhere in the vicinity. And there's been 4 times so far when we're convinced that we flew right through the reconnection region, and we were able to observe exactly what goes on there. And some of these things were predicted by theory, some were not. And so it's become even more fascinating than we thought. And it turns out that our instrumentation has more capabilities than we even, it must have been designed in, but we didn't believe it could do what it's doing. And that's why we're excited at this point. And so we have to target those regions, and we have to make three-dimensional measurements. So these spacecraft are deployed in a pyramid formation, and they travel around the Earth. When they get down to low altitudes, they string out into a line, and then when they go out to those two boxes I was showing, that's when they form this pyramid. And that's what we need, and you can see the pyramid forming, so we can go out and make these 3D measurements 100 times faster in the case of electrons than has been done before, and about 30 times faster for the ions. Now this shows that. Okay, so this is only a 2-second movie. Previous missions couldn't even get one of these sky maps of electrons in this 2 seconds. Here you're seeing 64 of them. And so this is a sky map of electrons from different vantage points. And but the interesting thing is that we can see what these electrons are doing, how they're taking energy from the magnetic field and turning it into particle energy. And this is what happens during a reconnection. And these are the other magnetic fields and other particles and electric fields that we're measuring and currents. So this is all that we have to do. But these are the things that are key, making measurements so much faster than before that we will definitely understand what makes reconnection work, and think this will be the last necessary mission of its kind. So I'm going to turn this over to Michael Hesse to explain more about magnetic reconnection.
Yeah, thank you, Jim. So I have the pleasure of explaining to you a little bit more about magnetic reconnection, why we care about it, and also to illustrate to you the challenges that we face with MMS to distinguish between prevailing theories that purport to describe how reconnection works. So let me start with continuing essentially where Jim already began, describing you the relevance of magnetic reconnection. Reconnection, we believe, is a very, very important process that powers dynamic processes in plasmas that range from astrophysical plasmas like jets and gamma ray bursts down to our more familiar environment, to the sun. And if we get this thing to, oops, that was a little too much. Okay, get this thing to work, then you will see a solar eruption. I guess you would see a solar eruption if this were working.
Scroll over it and click on it.
I'm trying. Okay, I guess it's not working. Okay, well, I will talk to it. What you're seeing here is a filament. This is a structure that the Earth is just a small fraction in size of this structure, and this can sit there for hours or days without any change, and then suddenly erupt and blast out into space. We're talking about billions of tons of mass that are then moving out into space at millions of miles per hour and running through the intervening medium, which, like the structure itself, is permeated by magnetic field and charged particles. This can then interact with the Earth, for example, or other objects, or planetary magnetospheres and their magnetic fields, and cause all sorts of interesting effects. Now, we believe that the power behind this is magnetic reconnection, and I will explain that to you in a little bit more detail as we go through this. Let me first show to you, however, what happens to the Earth's magnetic field if such a structure were to impact on it. And you're seeing this nice depiction of our, if you want, magnetic shield, and how that is influenced by, the sun would be on the left here, by material that the sun is throwing at it as part of such an eruption. Now, the changes to this magnetic structure, as you already saw in Jim's cartoon, are mediated by magnetic reconnection. You see the magnetic field changing here on the day side, and you also see it changing on the night side. And this change is magnetic reconnection. Now, there is a lot to this, and I want to explain that to you by means of a little bit of a theoretical model here, because magnetic reconnection transports charged particles, just as I showed you here, but it also converts energy. And energy, specifically, that's being converted is magnetic energy that's converted into other forms. You can store magnetic energy too. If you take two like poles of magnets and put them together and release them, then you have stored energy first and then you release that energy. Typically your magnets will fly apart. Now in space that happens too. It's just a bit more complicated. A model describes this in this way. What you're seeing here, the density of lines indicates the strength of the magnetic field that you have pushed together, if you like. And then if a process occurs in this region here, magnetic reconnection, then you see that the density of lines decreases. So the stored energy decreases, and I'll quantify that for you in a minute. And something new gets formed here along the lines of what Jim showed you earlier and what you also saw in my movie. Now let's quantify what I described here and the forms of energy. You get three forms of energy here. One is magnetic energy that is stored, and as a function of time, you see that decreasing because magnetic reconnection taps into this reservoir. Now it converts it into two different forms. One you see here in this blue line, which is increasing. That's internal energy. That might sound very complicated, but it's really nothing but heat. If you were converting this converting in the atmosphere, you would heat the atmosphere. Here you're heating the conglomerate of charged particles that permeate space. The other form of energy is kinetic energy here, which you see increasing here as well in form of this green curve. Kinetic energy is nothing but wind. Wind, like we have in the atmosphere, only here consisting out of streaming of charged particles. So you're converting magnetic energy that's stored in the magnetic field into these two different types of energies of the plasma. And that's, in that way, magnetic reconnection is arguably the most fundamental energy conversion and transport process in plasmas. And this, like Jim said, this occurs in these two locations. One is right here and one is right here. And MMS is designed to study this. And I want to now talk to you about how difficult it is and why we have to go through such small spacecraft separations to actually be able to measure it properly. So for this purpose, I'm going to turn this day side around to you. So I'm going to, half a year later, we're facing the other way. Okay, so I'll do that for you. At least I thought I would. Okay, now I am. So the Earth is here, the sun would be on the right. And as you have seen in that little sketch that I just showed you, as well as in the movie, reconnection occurs in some region out here. So the scale size of this is about 100,000 kilometers or 60,000 miles, if you prefer that. And if you blow up this region now, and now we're looking at predictions from models, you come down to a scale size of 500 kilometers, and you see these bright regions here, which are essentially currents where electrons essentially produce a current that's flowing here in this region. Now the real action is in a much smaller region still, and if you blow that up, you get to a scale size of only about 10 kilometers, and the layer here that we need to study is even thinner, of the order of a kilometer to a few kilometers thick. And we need to study that, and you see it has structure. That's why we need to study this by more than one spacecraft to understand properly its location and dynamics. And that's the reason, for example, why MMS is the closest spacecraft tetrahedron we've ever had, by far, down to about 10 kilometers. Now, if you want to resolve this structure, this, as you saw in the movie, this layer is not stationary. It wobbles around, backwards and forwards, typically at speeds of about 20 kilometers per second. And if you want to resolve a structure of only 1 to 5 kilometers thickness, you need to measure these electrons that Jim showed you with a time resolution of about 30 milliseconds. That's about 100 times faster than has ever been done. And MMS is designed and capable of doing that. In fact, Jim showed that to you. Another critical parameter here that we expect from theory to play a role is the electric field parallel to the magnetic field. And I show you a model prediction of that right here. You see this bright region here of enhanced parallel electric field. Now, if you have an electric field parallel to the magnetic field, it's like a voltage drop parallel to the magnetic field. And a charged particle likes to run parallel to a magnetic field, and it gets faster if there's a voltage drop. So you expect acceleration as a result of this parallel electric field, acceleration that you should be able to see if you measure particles. And I will show you the kind of subtlety that models predict we need to be able to measure in order to distinguish between different theories. So for that, it's important to distinguish this left-right direction and the direction along the magnetic field, which is into this plane in this plot. So what I'm showing you is what we call a distribution function. There's the velocity direction along the magnetic field, the velocity plotted here, and this is the left-right direction as a velocity. And these colors essentially denote the probability of finding an electron at this speed. okay? So this is a large negative speed here. This is the direction along the magnetic field. And you see this blob here is extended along the magnetic field, which means that particles have been accelerated from a velocity close to zero that they came in with to this extended structure along the magnetic field. But there's more subtlety here. If you're looking in this left-right direction, then if you look closely enough, then you find that there are more accelerated particles up here than there are down here, just very subtly so. And there are more, if you want, less accelerated particles down here than there are up here. This might sound very subtle, but it's very important for understanding how reconnection works, is to be able to measure the differences between those two sides. And MMS is designed to do that, and we have the best indications that we'll be able to verify or falsify this prediction. And to come back to the parallel electric field now, Katie Goodrich is actually going to show you some measurements of the parallel electric field that were obtained by MMS.
Thank you, Michael. So my name is Katie Goodrich. I am a graduate research assistant at the University of Colorado at Boulder, and I wear a couple of different hats on MMS. First, I'm a member of the Scientist in the Loop team, which is a team dedicated to looking at the most recent MMS data that comes down from the spacecraft and flagging very interesting or likely times of where we could see magnetic reconnection. I am also a member of the team that works on the Fields Instrument Suite. So the Fields Instrument Suite, which is shown in a schematic on the screen here, is an orchestra of instruments dedicated to measuring electric and magnetic fields. Now, it's important to get accurate measurements of magnetic and electric fields because they really interact with each other in very delicate ways. And I can go on forever about all these instruments, but I'm going to just focus on the probes that measure electric fields. And those are 6 probes that work in pairs that are one pair is along the spin plane of the spacecraft body, and another one is along the spin plane perpendicular to the other. And we have one more set of probes that are aligned along the spin axis of the spacecraft. Now, all these probes are put together so we can see 3-dimensional electric fields. And one thing that really this schematic doesn't capture are the lengths of these probes. Now, in the spin plane, the probes go out tip to tip 120 meters or 400 feet. So fully extended, MMS wouldn't be able to fit into a football stadium. And the probes along the spin axis of the spacecraft are 30 meters or 100 feet, which would fit roughly into a football field. And the reason we want these probes to be so far out from the spacecraft body is that the body itself have all these electronics on board that create their own electric fields. So it's necessary to be as far away from the body as possible to really capture the electric fields of the plasma. Now, now we have gone through, or the MMS team has gone through absolutely tremendous effort to capture 3-dimensional and highly accurate electric fields. And the reason we did this was because it is necessary to capture accurate measurements of parallel electric fields. Now, let me explain a little bit about parallel electric fields. In space, space is filled with magnetic fields and charged particles, and they interact with each other in a very specific way. In a typical or ideal plasma, you have charged particles traveling in a helical path along the magnetic field or parallel to the magnetic field or opposite of the magnetic field or anti-parallel. And with all these charged particles traveling up and down the magnetic field, any sort of electric field that would be created parallel to the magnetic field would be immediately shorted out. So there was a period of time where it was thought that parallel electric fields were non-existent in nature. However, that is not true. We have seen multiple observations of parallel electric field in what is called non-ideal plasma, And in a non-ideal plasma, there are processes that occur that Michael Hesse just talked about, where the population along the magnetic field lines can separate, creating a parallel electric field. And this can occur due to particle acceleration or a breaking of magnetic field. And it has become a very excellent indicator of high energy nonlinear processes in space physics. And magnetic reconnection is absolutely no exception to that. There have been multiple predictions of parallel electric fields in magnetic reconnection, and this is just an example of one of them. We fully predict to see parallel electric fields shown in blue and red in this diagram close to or along the center of magnetic reconnection, or the X line. Now, oops. This is an example of MMS data of magnetic field and electric field, and this is over 40 seconds. Now, this would be an event where a scientist in the loop would see and flag as a time of possible reconnection or a very interesting energetic phenomena. Now, magnetic field is on top, electric field is on the bottom, and parallel electric field is shown in red, where perpendicular fields are shown in blue and green. And what we see is a spacecraft traveling in space, encountering all these magnetic fields, and along the way, seeing all these spikes in parallel electric fields. And at the moment of the sharpest change in magnetic field, we see this gigantic spike in parallel electric field, 130 millivolts per meter, which is maybe 10 times the size we expected to see. Now, with MMS, we can actually zoom into this particular spike. And this is over 5.5 seconds. Remember, we just saw 40 seconds. And this spike that I just showed you before is not just a singular spike. It's actually a series of very high amplitude spikes that all occur on the time frame of a millisecond, which is just a snap. So with this MMS spacecraft, we can see really high energetic nonlinear processes that occur just in the time frame of a snap, which is incredible. And more data like this is coming down every single day, and we on the MMS team are so excited to be seeing this data and unlocking all this mystery. Now, I believe Ian Cohen will now talk about energetic particles.
Hello, my name is Ian Cohen. I'm a postdoctoral fellow at the Johns Hopkins University Applied Physics Laboratory, and I have the privilege to talk to you about energetic particles on MMS. So I'm part of the energetic particle detector, which is actually a suite of instruments. Unfortunately, this is a little skewed here, but the EPD suite is made up of two different instruments, the Fly's Eye Energetic Particle Sensor, or FEEPS, and the Energetic Ion Spectrometer, or EIS. Unfortunately, the diagram here is slightly skewed, so I won't be able to show you the details of the instruments, but the Fly's Eye Energetic Particle Sensor gets its name, the Fly's Eye, because it has multiple sensors, 9 on each, that look in different directions simultaneously, so it can get extremely rapid and full sky coverage of these energetic particles nearly simultaneously, utilizing 2 different FEEPS instruments on each of the 4 spacecraft. Now, the complement to that is the energetic ion spectrometer, which works like many other energetic particle detectors that have been used on a similar spacecraft. But what this adds to the complement is mass spectrometry. So it basically allows us to identify the different species of ions, hydrogen from helium, from oxygen, as we move through the orbit. And as you can see here, we have they're outlined. So we have 2 FEEPs, one on each side, face of the spacecraft, top and bottom, and then EIS in the middle. And together, as we spin, we use those 3 instruments in complement to get extremely rapid and nearly full sky coverage of the energetic electrons and ions. And it's not just, so Katie talked a lot about the fields measurements, but we also need to look at the particles. And it's not just the energy of the particles and where they're coming from, but we need additional information as well. And very important to that information is the angle of the particles relative to the fields. So in particular, one of those measurements is known as the pitch angle. So this is the angle that the particles are moving relative to the magnetic field. And in what we're going to be talking about next, what's really important is whether those particles are moving parallel, so in the same direction as the magnetic field, or anti-parallel, opposite to the direction that the field's pointing. So this is a diagram that you've seen several times now of the magnetic field of Earth. But what I'm really going to focus on are these purple lines that are slightly farther away from the box of reconnection that Jim and Michael identified earlier. And what I really want to highlight to you is that as we move away from the site of the local reconnection, we still have these purple field lines that are connected across the boundary here known as the magnetopause. That's the furthest region where the boundary between the Earth's magnetic field and the interplanetary magnetic field coming from the sun. And what you'll notice is that in these circles, and as I've indicated here, we still have field lines crossing through the magnetopause. And if we blow that up, we can see as you get close to the reconnection region, you get these field lines that bend across the magnetopause. And you can see that little region right there allows a field line, a trajectory, avenue for particles to actually get across the magnetopause and out of the magnetosphere proper, basically escape from the magnetosphere and the Earth environment. So we know, and it's been shown, that ions and electrons, so energetic particles from within the magnetosphere, so here's Earth, the sun would be up to the top here, these energetic particles can drift. They're influenced by the electric and magnetic fields, and they can drift, ions going one way because they're positively charged, electrons going the opposite way because they're negatively charged, and they can make it all the way around the Earth towards that magnetopause, that boundary. And if reconnection has occurred and it's opened up a reconnected field line that crosses across the magnetopause boundary, that allows an avenue for those energetic particles to get out of the magnetosphere where they can then travel, escape freely across the interplanetary magnetic field. So we've shown with simulations that if you don't have reconnection, if you don't have that reconnected field line creating an avenue across the magnetopause, that the drifting particles, in this case an ion, they drift to that magnetopause, that boundary between the Earth and solar magnetic fields, and they get trapped at that boundary. They're not allowed, they don't get out, they can't escape. However, if you have reconnection and you have that reconnected field line providing an avenue across the magnetopause, then you see that drifting ion comes, encounters the magnetopause, and is able to get across it and ultimately escape out into interplanetary space. So now comes the exciting part. Preliminary, never before seen, as yet unpublished MMS data that you get to see for the first time today. So on the left is a pictorial representation, and on the right is the data. So I'm going to walk you through this here. On the top panel, we have the magnetic field. Again, like Katie said, similar to the electric field, these are measurements that are taken at an extremely high cadence, higher than have ever been taken before. And as we move through, so on the left in the data here, we are in the magnetosphere, so we're on the Earth side of that magnetopause boundary, and we're moving outwards, away from the Earth. As we come towards the magnetopause, which is indicated with this black line, that's our boundary. So we're moving in both spatially outwards and also in time. As we get to that boundary, you'll notice we cross and then we lose many of those, the particles that we're seeing on the magnetospheric side. And plotted here are the single channel of energetic electrons and energetic protons, or hydrogen. And you'll notice that on the y-axis is the pitch angle. So basically, the top half of these plots show particles that are pointing opposite to the magnetic field, and then the lower half is showing particles that are parallel to that magnetic field. And as we transition out towards this boundary, you'll notice we're moving from field lines that are connected on both ends to the Earth. So basically, we have both parallel in red and anti-parallel in purple particles bouncing back and forth. And as we move from that unconnected Earth field line to a reconnected field line that's across the magnetopause boundary, we lose all of the purple anti-parallel particles and only have escaping parallel particles. And now if we look at the data here, you can see that exact transition shown in the data. We have the full, both parallel and anti-parallel particles, and as we move towards that boundary, we start to lose the higher pitch angle, or the anti-parallel particles, And then once we get across that boundary, the only things that persist are those escaping parallel particles. So this is extremely exciting, and it means that we both have shown that we have reconnection, because the only way that these particles can get out into the out of the magnetosphere is if those reconnected field lines have provided that avenue for them to escape. So we can show that we have there has been reconnection, and B, we're also showing that that reconnection, that avenue across the magnetopause, persists at large distances from the actual localized point where reconnection can occur. And I think with that, we're ready to take your questions.
We will now open up to questions from any reporters who are in the room. Are there any reporters in the room who have questions? Please raise your hand. No? Zoe, are there any reporters on the chat with questions? No? I do want to mention that there is a virtual reality headset that people can try on that features the MMS mission. So see that gentleman over there. Thank you. That concludes our press workshop and our press events for the 2015 fall meeting. Thank you.